Okay, I'm going to start. I'll send out an announcement that there will be some more online activities. A week from today, you'll have your next test. We are, I would say, ahead of schedule. And so next week, we'll have some review lessons, no new material. I'm not planning to have any live Zooms next week. Okay, everything will be recorded. And then the test, I'll send further information about that. I'm going to share my screen. Okay, so we're going to look at reactions of alkenes. And again, this is a summary of three principal types of reactions. We have addition, elimination, and substitution. We've looked at substitution and elimination, at least some types of substitution and elimination in the previous two chapters. In this chapter, we will look at addition, which is just the opposite of elimination. In an addition reaction, we decrease the bond order between the carbon atoms. So that generally involves going from a double bond to a single bond. Chapter after this, we'll look at alkynes, and those are also subject to addition reactions. Okay, here's the basis for the reaction of alkenes, and that is this pi bond. Okay, because of the pi bond, we have an electron-rich region, and the pi bond will attack electrophiles, electron-deficient species. Okay, this is the pattern for most of the reactions, but not all of them in this chapter. Double bond attacks the electrophile. Okay, we get a carbocation. Okay, we'll have some reactions that won't fit this pattern, but then a nucleophile then attacks the carbocation. Okay, here's a summary of the different types of addition reactions that we'll be looking at. Okay, this is hydration. This is just backwards from what we did in lab yesterday, which was dehydration. Okay, that follows the pattern shown on the previous slide. Hydrogenation is a different type of mechanism, but again, it's an addition. Okay, dihydroxylation is both an oxidation and an addition, where we form this vicinal diol, also called a glycol. We'll look at a couple of methods of oxidative cleavage where we actually break the carbon-carbon bond. Epoxidation is a type of addition. It's also an oxidation. We'll look at halogenation, halohydrin formation, where X is some halogen. Hydrohalogenation, addition of hydrogen and the halogen. And then we'll look at cyclopropanation. Okay, starting off with addition of hydrogen halides to alkenes. Step one is protonation of the double bond. The protonation forms the most stable carbocation. Okay, so this is a regioselective reaction if the alkene is unsymmetric. In step 2, the nucleophile attacks the carbocation and forms a new covalent bond. Okay, HX can be HBr, HCl, or HI. Okay, so the double bond attacks the hydrogen, and this is symmetric, so it doesn't matter which side the hydrogen goes to. Okay, since this pair of electrons moved on to the bromine, it becomes negative, and then opposite charges attract. We always go negative to positive. So bromide will donate a pair of electrons to the carbocation and will form a new covalent bond. Okay, if the alkene is unsymmetric, we can predict the product isomer using Markovnikov's rule. Right, Markovnikov's rule originally said that whichever side of the alkene had the most hydrogens would get the hydrogen. Okay, we'll look at a couple of reactions which appear to violate Markovnikov's rule. But if you consider that we're forming a product in which the most stable intermediate influences the particular positional isomer, then that takes into account. That takes that into account. Okay, here we have an unsymmetric alkene. And so we can predict that the rich get richer when it comes to hydrogens. Okay, so carbon 2 has no hydrogens, carbon 3 has 1. So the hydrogen will go to carbon 3, which gives us a tertiary carbocation, which is more stable than a secondary. Okay, so this carbocation is not formed, and so this will then go on to product. Bromide will attack the carbocation, as shown here. Right, so this is the product we'll get. Right, formation of the tertiary carbocation is faster. It has a lower activation energy, and also you can see from the diagram that it is more stable. It's lower energy. Okay, here's another example of Markovnikov's rule. This is 1-methyl cyclohexene. Hydrogen would go to carbon number 2, okay, the side that's richer already. And then bromide attacks, and our product is 1-bromo, 1-methyl cyclohexane, and not the other isomer. Okay, and that's what this is showing. Okay, here are a few more examples. Okay, this is similar to what we had before with HBr. Okay, hydrogen would go to carbon number 3, chlorine would go to carbon number 2. Okay, with this bicyclic compound, this position is richer in hydrogen, so that would get the hydrogen. The other site would get the chlorine. Okay, same way with this. CH2 gets the hydrogen. The one position on the ring gets the iodine. Okay, next we will consider one of two reactions that appears to be anti-Markovnikov. Okay, instead of the rich get richer, the poor get richer. This is the Robin Hood reaction. Okay, so in the presence of peroxides, HBr adds to an alkene to form an anti Markovnikov product. Okay, and this was something that was actually discovered accidentally in the laboratory. The researchers were getting unexpected results, and they found that their alkene was contaminated with peroxides. All right, peroxides form free radicals. So this is a little bit different mechanism, but this only works with HBr. Okay, only HBr has the right reactivity for each step of the free radical chain reaction to take place. Okay, the peroxide effect is not seen with HCl or HI. Okay, so if you have HCl or HI with peroxides, the peroxides don't make any difference. You're still going to get the Markovnikov product. The reaction of the alkyl radical with HCl or HI, it turns out, is strongly endothermic. Okay, so here's how it takes place. Here we have a peroxide, and with the presence of heat or light, the oxygen-oxygen bond is very weak, very easy to break. It breaks symmetrically or homolytically, and we get two alkoxy radicals. Okay, this is the delta H for that process, 150 kJs. Okay, so this step is endothermic, and then hydrogen is abstracted from HBr, okay, which is not shown on the next page. I'll go ahead and draw that on the board. Okay, so we have an alkoxy radical, and this alkoxy radical removes a hydrogen from HBr. So what happens is this bond will split up. Okay, we use a single barbed fish hook arrow. We'll get ROH, and then we'll have an unpaired electron left behind on the bromine. So we have a bromine free radical. Right, this bromine free radical then attacks the alkene. Okay, so in the pi bond, one electron pairs up with the bromine to form a carbon-bromine bond. The other electron is left behind on this carbon, so we generate a free radical. So that's a propagation step. And then from an HBr molecule, this free radical removes a hydrogen. Okay, notice as we go back here, H actually goes to carbon number 2, not to carbon 1. And the reason is that gives us the more bromine goes to carbon number 1. Let's try that again. Bromine goes to carbon number 1, which gives us the more stable secondary free radical. Okay, this free radical then can abstract a hydrogen from HBr, and this is our product. Okay, we could also have a termination step where this free radical joins with a bromine free radical. Okay, but we get the anti-Markovnikov product, and that's because the more stable secondary free radical is formed. Okay, so with 2-methyl-2-butene, when we add bromine to carbon number 3, that gives us a tertiary free radical. Adding a bromine to carbon number 2 would give us a secondary free radical, which is less stable. Okay, and not only is the tertiary radical more stable, but it's also formed faster. Okay, so without the peroxides, bromine would go here to carbon number 1. But with the peroxides, bromine goes down here. Okay, let's look at hydration of alkenes next. Okay, this is just the reverse of what we did yesterday in lab. Instead of removing the elements of water, we're going to add the elements of water with an acid catalyst. Now to go the reverse direction, we would want a low concentration of water. And that's what we did. We used concentrated sulfuric or phosphoric acid, and we removed the water. Okay, if we're going the reverse direction, we would want an excess of water. Water is not acidic enough where the alkene can readily protonate it, okay, unlike something like HCl or HBr, which has a very acidic hydrogen. Okay, so you have to have an acid catalyst, and usually this is something like sulfuric acid. So down here in bullet point number 4, it uses a dilute solution of sulfuric or phosphoric acid, okay, rather than a concentrated solution like we did yesterday. Okay, this does follow Markovnikov's rule if we have an unsymmetric alkene. All right, so here's the mechanism. Sulfuric acid reacts with water to form hydronium ion, okay, which of course is a stronger acid than water. The alkene picks up a hydrogen. We form the more stable carbocation. And then water attacks, not hydroxide, because remember we're doing this in dilute acid solution, so the hydroxide concentration would be very low. Okay, so water attacks, we get this oxonium ion, as it's called. Okay, we have excess water. Water removes this proton, and we get an alcohol, and then we regenerate our hydronium ion catalyst. Okay, this is a Markovnikov reaction. Okay, we form the more stable, in this case, tertiary carbocation. Okay, since we're going through a carbocation intermediate, rearrangements are possible. Okay, so let's consider 3,3-dimethylbutanene, okay, and 50% sulfuric acid. Okay, this is actually the major product. Okay, not the one with the alcohol on position number 2 here. Okay, so we start out, the alkene gets protonated, hydrogen goes to carbon number 1, we have a plus charge on carbon number 2, and if we do a methyl shift, or methyl moves along with its pair of electrons, we go from a secondary to a tertiary carbocation, okay, which is more stable. Okay, then water attacks, and another water removes a proton, and we get this alcohol. Okay, this is another method of making alcohols from alkenes. This is called oxymercuration, demercuration. Okay, so we start out with mercury 2 acetate. And the intermediate is this acetoxymercurial alcohol. And then using NaBH4, this is called sodium borohydride. Sodium borohydride removes the mercury and replaces it with a hydrogen. Okay, this does follow Markovnikov's rule. Okay, so hydrogen goes to the side that is richer in hydrogen already. OH goes to the other side. This can take place under milder conditions than direct hydration, which is what we saw in the previous few slides. There is a significant advantage to using oxymercuration, demercuration, and that is that no rearrangements or polymerization occurs. Okay, one disadvantage, of course, is that you're using mercury, which is toxic. Okay, so this reaction utilizes mercury 2 acetate, which dissociates slightly to form Hg acetate plus. Okay, the acetate what that is this. That's the acetate group. Okay, so this will dissociate slightly to give acetate and Hg monoacetate plus. Okay, that will add to the pi bond, and it forms a 3-membered ring called a mercurinium ion. Okay, so here is the dissociation that takes place. Okay, so the alkene attacks the mercury. The mercury has a lone pair that can attack the other side, and we get this 3-membered ring. Okay, this 3-membered ring prevents a hydride or methyl shift, and so that's why we don't have rearrangement or polymerization. All right, in the next step, water attacks, and if this was originally an unsymmetric alkene, the water would attack the more substituted side. And this is very similar to an SN2. Okay, water attacks, and we form a bond between carbon and oxygen, and at the same time we break this bond to mercury. Okay, this bond to mercury is not broken. And since we have excess water comes along and it removes this extra hydrogen. We get this organomercurial alcohol and hydronium ion. All right, and then the next step, and we're not showing the mechanism here, the next step involves sodium borohydride, which replaces the mercury with a hydrogen. Sodium borohydride, it turns out it also reduces mercury 2 to mercury 0, that is elemental mercury, in the process. Okay, so this gives the Markovnikov alcohol. The hydroxy group is on the most substituted carbon. Okay, so this is the same alkene that we saw earlier. All right, this one right here. Okay, and we saw rearrangement took place with simple hydration. Okay, we formed the mercurinium ion, the three-membered ring. Water attacks the more substituted side, and we remove a proton, and then we reduce with sodium borohydride, and then we get the unrearranged alcohol. Alkoxy mercuration, demercuration, is similar to oxymercuration, demercuration, except that we use an alcohol as the solvent and the nucleophile instead of water. And when we use an alcohol, we'll get an ether rather than alcohol as the product. Okay, it's the same mechanism. Mercury bridges the double bond, the two carbons of the double bond. The alcohol attacks. Another alcohol removes this extra proton, and then sodium borohydride replaces the mercury with a hydrogen. Okay, if we were attempting to prepare this compound, one methoxy, okay, OCH3 is called the methoxy group, 1-methoxy, 1-methyl cyclopentane. Okay, we could start out with 1-methyl cyclopentene using mercury 2 acetate and methanol and sodium borohydride. This would give us the correct isomer. Okay, this is the other reaction which appears to violate Markovnikov's rule. But if we look at the extended version of Markovnikov's rule, again, this will proceed through the more stable intermediate. Okay, so hydrogen does not go to the side that's richer in hydrogen, it goes to the other side. And so we call this anti-Markovnikov orientation. Okay, so H.C. Brown of Purdue University, okay, who won the Nobel Prize back in the 1970s, he discovered that diborane, B2H6, adds to alkenes with anti-Markovnikov orientation to form alkyl boranes, which after oxidation give the anti-Markovnikov alcohols. Okay, so we first form the borane, and then using oxidation with hydrogen peroxide, we produce an alcohol. Right, diborane is a dimer of BH3, which is borane. Borane is extremely reactive. It spontaneously dimerizes. And diborane is the more stable form. Diborane is not used as much anymore. It is, it's a gas, and so it's more difficult to measure out diborane. Also, if diborane comes in contact with oxygen in the air, it will spontaneously ignite. So it's dangerous as well. Okay, a much more convenient way of doing hydroboration is to use a borane THF complex. Okay, by reacting tetrahydrofuran, which is a cyclic ether, also called THF, with diborane, we form this complex. Okay, this is in solution, and it's very convenient to order BH3-THF solutions of whatever molarity you want. Okay, so if you have a 1 molar solution, that's very convenient. If you want so many moles of borane THF, you measure out the appropriate volume. Okay, so here is the mechanism of hydroboration. Okay, the key difference here between this and, say, HCl is the polarity of the starting material. Okay, if we consider something like HCl, okay, we know that chlorine is much more electronegative than hydrogen. Okay, so hydrogen is electron deficient. It has a partial positive charge. Borane, on the other hand, actually has the opposite polarity. Okay, so here, hydrogen is partially negative. And not only that, the alkene group is nucleophilic, and so instead of attacking the hydrogen, it's going to attack the boron. Boron also lacks an octet, so it's a very good electron pair acceptor. Okay, so the alkene attacks the boron. We go through this square transition state where hydrogen is added to the adjacent carbon. So boron goes to the less substituted carbon. You get this alkyl borane. And this particular orientation places the initial partial positive charge in the transition state of the more highly substituted carbon atom. Okay, so if we look at this square transition state, the partial positive is on the more substituted carbon atom. Okay, so this transition state is much less stable. All right, once the hydroboration has taken place, then using hydrogen peroxide in basic solution, we obtain the alcohol. And the orientation is anti-Markovnikov. Okay, since borane has 3 hydrogens, the stoichiometry is such that 3 moles of alkene can react with 1 mole of borane. Okay, so before we do the oxidation, we actually have a trialkyl borane. Hydroboration is also stereoselective. Okay, we get a particular stereoisomer. And the primary place that you would see this would be if you had a cyclic alkene. Okay, so here we're starting off with 1-methyl-cyclopentene. H goes to the side with the fewer hydrogens. OH goes to the other side, so we get the anti-Markovnikov. So it is regioselective. We get the anti-Markovnikov. It's also stereoselective in that H and OH are added syn to each other. Okay, they're added to the same side. Okay, since we are generating two new stereocenters, we'll get a racemic mixture of enantiomers. Okay, this is what happens when we add the basic solution of hydrogen peroxide. Okay, first we have an acid-base reaction that occurs where hydrogen peroxide is deprotonated to form the hydroperoxide ion. Hydroperoxide then attacks boron. Okay, one of the alkyl groups, one of the R groups, migrates onto the oxygen, which gives us what's called a borate ester. And this happens 2 more times. We have a trialkyl borate ester. And then OH comes in and it displaces the OR groups. Okay, in this problem, show how you would convert 1-methyl-cyclopentanol to 2-methyl-cyclopentanol. Okay, so starting off with 1-methyl-cyclopentanol. Okay, what we could do is we could first dehydrate to form the alkene. And then we could do a hydroboration oxidation. Okay, this is another example of hydroboration. Okay, we obtain an alcohol. In this case, it's symmetric, and it turns out that the H and OH are added cis to each other. They're added to what is called the exophase. Okay, that is above the bicyclic system rather than the endo. Okay, we see that when these are labeled with deuterium. All right, next we'll look at addition of halogens. And we're going to do a lab in the next few weeks where we'll do a halogenation and then a dehalogenation reaction. Okay, if you start off with an alkene, and you can add chlorine and bromine and sometimes iodine, and you get this dihalogenated compound. Okay, with iodine, oftentimes you have to heat it because the reaction is slow. Okay, in the case of bromine, okay, this reaction takes place almost immediately at room temperature. Okay, it takes place very quickly, and the addition is usually anti. Okay, when a nucleophile, such as an alkene, adds to the bromine, attacks the bromine, we get a three-membered ring, a bromonium ion, okay, rather than an open carbocation. The bromide that was formed, the Br minus or X minus, then attacks from the backside. And when it does that, we form a bond, we break a bond at the same time. Okay, nothing happens to this bond, so that's still there. And since X minus attacks from the backside, and we have this three-membered ring, the stereochemistry is trans. So we get trans, we don't get a mixture of cis and trans, we don't get cis, we just get the trans. Okay, so here's a example using the cyclic structure cyclopentene. Okay, we end up with the trans 1,2-dibromo cyclopentane plus the enantiomer. Okay, so bromide could attack from this side or this side, which would give the enantiomer of this. Okay, since the reaction is stereospecific, we're starting with cis-butene. We'll get two enantiomers. We'll get a racemic mixture of two enantiomers, plus minus 2,3-dibromobutane. If we use the trans, we actually get the meso. Okay, and the reason in both cases is because of the bromonium ion. Okay, because bromine adds rapidly to double bonds, we can use bromine solution as a simple test for the presence of alkenes. Okay, so Br2 is in a solution of carbon tetrachloride, or we can use methylene chloride. And what happens is that the bromine starts out as this dark red brown color, and the dibromoalkane which is produced is colorless. And so we'll see a almost immediate decolorization of the bromine. Okay, if there's no double bond, as shown on the right here, the red-brown color will persist. But if there's an alkene, we'll see disappearance of the bromine color. Okay, this is the final reaction that we'll go over today, and that is halohydrin formation. Right, this reaction is both regioselective and stereoselective. Okay, if instead of a solvent such as carbon tetrachloride or dichloromethane, we use water, instead of a dibromo or dihalogenated alkane, we'll get a halohydrin. Chlorohydrin if our halogen is chlorine, bromohydrin if it's bromine, iodohydrin if it's iodine. Okay, water, in this case, is the nucleophile. This is a Markovnikov addition. The bromide adds to the less substituted carbon. Okay, so this is how it takes place. It starts out just like the previous reaction. We'll form this three-membered ring, this halonium ion, and then water attacks. Okay, why not the halide? Well, it turns out that these halogens are not very soluble in water. And so there is a very low concentration of the halide, and there's a very large amount of water molecules. And because there are so many more water molecules than there are halide ions, water acts as a nucleophile. We have a large excess of water, so water then deprotonates this oxonium ion, and we get the halohydrin. Okay, it's regioselective because the alcohol will end up on the more substituted side. It is also stereoselective because the halogen and the OH are anti to each other. Okay, so if we're using cyclopentene, the product will be the trans 2-bromocyclopentanol. Okay, we haven't talked about alcohols yet, but alcohols will take priority in naming over halides. Okay, so that's why the alcohol is on number 1. Okay, if we had a methyl instead of a hydrogen here, the OH would end up on the side with the methyl, the more substituted side. Okay, the alcohol and the bromine are trans to each other. Okay, here's a chloronium ion. Again, water adds, and it gives the Markovnikov product. Okay, here's that example with the methyl. Okay, water goes to the more substituted side, so that's where the alcohol ends up. Bromine goes to carbon number 2. Alcohol and bromine are trans to each other. Okay, I'm going to go ahead and stop there. Okay, as I mentioned right at the beginning, we won't have any live Zoom, just recorded Zoom next week, and it'll be entirely review. Your test will be on Friday. Okay. So I will see you later.
Thank you.
Okay. Did you have a question?
No, I just said thank you.
Okay, you're welcome.